Okay, so in this section, we're going to talk about equality constraints using the, Lagrange multipliers. Okay, so we have an equality constraint. In other words, what we're trying to do is we're trying to minimize f of x subject to the constraint that h of x is equal to 0. And h is a vector of constraints. So, let's gain a couple of insights here. So insight number one, first of all, geometrically, what do these constraints look like? So if h is linear, then we get something like this. H of x, would be some matrix h times x equal to 0. And h would map Rn into Rm. And this constraint means that x has to be in the null space, right? So x is in the null space of h, which is a linear space of dimension n minus m. Remember, the range space of h transpose is going to be m-dimensional. And so this thing is well, assuming it's full rank, then this would be a linear subspace of dimension n minus m. Or it's an n minus m dimensional hyperplane. In general, h of x will be an n minus m dimensional hypersurface. And so, like, for example, what do we mean by hypersurface? If this is x1, x2, here's a one-dimensional hypersurface. So we might have a, an optimization problem where you're trying to optimize something, and we are constrained. So the constrained optimal would be constrained to the hypersurface. So the constrained optimal would be right here. That would be x plus. So it's the, we try to minimize f subject to the constraint that h of x is equal to 0. Means that we lie on this m minus n dimensional hyperplane. Okay, second insight is that at a constrained minimum, the gradient's orthogonal to the hypersurface. So we have this hypersurface. Let's think of it as linear for a minute. And if we look at the gradient of f, so here I've drawn the gradient as being a local maximum, but the gradient could, if it was a local minimum, it would go in the opposite direction. But notice at this point, so this is, remember, the gradient is orthogonal to the tangent plane of f, so the gradient's going to point in this direction. But right here, the gradient points, in, and it turns out that, this hypersurface is going to be, there's some level curve at which it's tangent, right? And that's going to actually be the smallest level curve, because as we move out here, we get bigger and bigger level curves, right? So the local minimum, the local constrained minimum, is such that the gradient is orthogonal to this hypersurface. And that it's also going to be true, for example, if it was a a nonlinear function like that, right? If this is a local minimum, then the gradient of that, or it could point in the other direction, it's going to be orthogonal to the tangent plane of the hypersurface. Okay, so we're going to use these insights essentially to help us derive solution techniques for constraint optimization problems. Okay, so we need to have some definitions and sort of formalize things a little bit so that we can talk about these problems correctly. So let's let S be our hypersurface. So that's this surface, let's say, is S. and it has dimension n minus m. And now you think of a curve on this hypersurface. So let's let x of c be some curve, and there could be other curves, but it's just some curve parameterized by c. This is the Greek x. Okay, so there's some curve, and what we can take the derivative. So at any point x naught, we can take the derivative of the curve by taking, the derivative of x with respect to xc, and it's the derivative of this curve would, point tangent to the curve at every point. Okay, so the tangent plane, here's the definition. The tangent plane, how do we define the tangent plane to a hypersurface at some point x? So the tangent plane to a surface S at x is the span of the derivatives of all the differential curves on x. So if we go back here, you can think, this, we get one tangent vector, and then we have another curve. We get another tangent vector, and we get another tangent vector. Now, if I take all possible curves, right, and look at their tangent vectors, and then I take the span of all those vectors, okay, it's going to define a plane. And the plane is going to be, there's this hyperplane that comes right through there, and it's going to be a hyperplane that is tangent to all of these vectors will basically be tangent to this surface. So this plane would be a tangent plane at x. So this is the standard way of defining a tangent plane through, this isn't a computational method, but it's a theoretical method. It's the span of the derivatives of all the differential curves on S at that particular point x. Yeah, the problem with this definition, it's not constructive, but it gives us, it doesn't give us a good way to actually construct the tangent plane. That's okay, but it helps us to define what the tangent plane is. To construct the tangent plane, we recall that the gradient of h is going to be orthogonal to all your level curves of h. So remember, what's the formula for a plane? This is going to be, a plane at x star. We could write this, some plane at x star. It's going to be the set of all y's, and the plane, I guess, is parameterized by this n vector. Yeah, maybe I could write, this is a plane at x star, and it's parameterized by n. It's going to be equal to this set. It's all the y's. So here's x star, here's n. Here, that would be, if this is y, then this vector here would be y minus x star. It's all those vectors that are orthogonal to n, right? Because if y is out here, it's not orthogonal, so it doesn't satisfy this. All right, so yeah, so the tangent plane is this set of all y's, that x is, so that y minus x is orthogonal to this vector n. Okay, so what is the tangent plane of h at x? It's going to be, remember, we know that the tangent plane, this tangent plane is going to be orthogonal to the gradient vector. So that tells us that the tangent plane of h at x star is going to be, it's the set of all y's. So this is just, our previous equation for a plane. It's going to be the set of all y's, so that y minus x star is orthogonal to the gradient of h. And remember, the gradient of h. This is an n minus, it's a this is going to be, I guess, an m-dimensional vector, and so this plane is now an n minus m dimensional plane, as long as the rows of h are linearly independent. So we need some condition that says, okay, the rows of h are going to be linearly independent. So if we look at the gradient vectors, if you look at the gradient of h1, gradient of h2, because remember, gradient of h, let's just kind of recall what we have here. So remember that h is equal to h1 of x, down to hm of x. So when I look at the partial, this del h, we're defining that to be the partial of h with respect to, of h1 with respect to x1, partial of h1 with respect to x2, up to partial of h1 with respect to xn, down to partial of hm with respect to x1, partial of hm with respect to xn. And we could write this guy as, I suppose, del h1 transpose, del h2 transpose, down to del hm transpose, where del hi is going to be the partial of hi with respect to x1 down to partial of hi with respect to xn. Remember, when it's a row vector, or when it's a vector, we make it a column vector. So, and then when it's a vector function, we basically have these vectors on the row. So we have to have the transpose like that. Okay, so we want, each of these rows define a new, so like if we said del hx equals to, this is an x star, so we want to have we want to look at all the tangent planes where this is, we want, in other words, we want a tangent plane that's orthogonal to each of these guys. So we're going to have del hi y minus xi equal to 0, set of all y's in Rn. Okay, that would be the tangent plane, associated with this curve, and we collect all of those together, I equals 1 to n, and that gives us the tangent plane at x star. So we need each of these rows to be linearly independent. Okay, and that brings us back here. So if the gradient vectors, again, these now are, since the rows have a transpose, these guys are all column vectors. So each of these vectors are independent at x star, meaning when we evaluate these guys at x star. If they're linearly independent, we say that x star is a regular point. Okay, so and then we say h is regular if every point is a regular point. Okay, and we always assume that our constraints are regular, meaning that basically what it means is that if we have one curve that looks like that and another curve like that, these these gradient vectors are going to be linearly independent. So constraints that would not be regular would be if I had a constraint that looked like this and another constraint that looked like that. At this point, their gradients kind of align. They're not linearly independent. So these kind of constraints would not be regular this would not be a regular point. So they, in general, the functions would not be regular. All right, so our constraints, we have to assume that our constraints are regular. All right, so this is Moon chapter, or Lemma 18.1. If x of c is a curve on this n minus m dimensional hyperplane, so that x of c at 0 is x star. So in other words, what we're doing is we've got our, s kind of does this, and so we now have a curve, and we parameterize it so that this is x of, x star is equal to this x of 0. We have this curve that is x of c, and we just shift c so that right at x star, that's where the 0 point is. Okay, we say that, and suppose that this is our local minimum. Okay, then we have to have the derivative of f of x. The derivative with respect to c of f of x c at c equals 0 has to be 0. So in other words, if we here's x of c, and then there's also, this, I guess maybe here's our picture down here. We have f, and here is our hypersurface. And so in the one-dimensional case, x of c would just run along this hypersurface. Now what we're saying is that that the derivative with respect to c of f of xc. See, notice that as I move along here, f is changing. It's decreasing, 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 decreasing. And then right here, it stops decreasing and starts increasing. So now if I take the derivative, see, the derivative of f of x of c up here is going to be negative, 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 0, positive, 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 positive. So this lemma says that at a constrained minimum, this guy is equal to 0. Okay, so that's what it's saying. All right, so proof, well, we expand in terms of a Taylor series. So f of x of c, we expand around f of x, basically around x star. So that's going to be f of x 0. And then I'm going to have the derivative of f of x of c at x equals 0, d dc, times my small deviation c. And then I've got higher order terms. And if f of x of 0 is a minimum, then this minus that has to be positive. So this guy has to be positive for every c, both positive and negative. And so because it has to be true for every c, positive and negative, this thing itself has to be equal to 0. And we could have written df of x of c, ddc of f of x of c. By the chain rule, it's going to be the partial of f with respect to x times dx, really. Yeah, this is, I should have written this as, dx of c. And dx of c is an element of the tangent plane. Okay, here's another lemma. If x star is a regular point of h of x and a local constrained minimum, so this is a necessary condition. So we know it's a regular point, we know it's a local constrained minimum, and we're assuming a regular point. Then the gradient of h, x star times y, is equal to 0 In other words, if the gradient of h is orthogonal to y, then the gradient of f is also orthogonal to y. In other words, if y is in the tangent plane of h, then y is orthogonal to the gradient. And again, the picture looks like this. You have at this local constrained minimum, the gradient points, orthogonal to the tangent plane of f. And we also know that at a local constrained minimum that that h aligns with f. And so we're going to have, this tangent plane has to be orthogonal to both the constraint in y, and also the gradient of f, the gradient of the constraint, and the gradient of the function. So in other words, the gradient of the constraint and the gradient of the function have to line up with each other. Okay, so we could, to prove this, we could translate the coordinate system so that x star is equal to 0. And then what does regularity imply? It means that if we look at this plane at x star as the set of all z's, so that the gradient, that z is orthogonal to the gradient, and then pick a y that's in that plane. So we know that this is true. That's by definition. Now choose a smooth curve of x of c on the hypersurface h of x equals 0, so that x of 0 equals x star. Then dx, like the derivative, this would be dx at 0 is going to be some y. And then we know from the previous lemma that it has to be orthogonal to the gradient, because we know that df is equal to 0. Okay, so here's the takeaway. At a constrained local minimum, the gradient of f and the columns of the gradient of h are parallel. So there's some, in other words, they're linearly dependent. So there's some scalar so that the gradient of f is going to be some scalar of the gradient of h. And this is true for every one of these vectors of h. So I could sum, right? It's going to be a linear, in other words, the gradient here is going to be some linear combination of all of your mu i's. And in other words, I sum all of these guys and I get this. M is just, I sum over m of the ui's. And so then I could divide by m, and I'm going to get, and then I move this guy to the other side, and I'm going to get the gradient of f minus some scalar times the gradient of h is equal to 0. So if I put h back in its matrix form, now we have the columns, right? So this guy here, oh, I'm sorry. Yeah, these are going to be the rows of h. Yeah, times each of the lambdas. So so lambda would be, these sets of coefficients. And this equation, I could rewrite it as the gradient of f at x star plus the gradient of h times lambda is equal to 0. So if at a constrained local minimum, we have that this is true. Okay, now these vectors lambda are called the Lagrange multipliers. All right, Moon Theorem 18.3. This is the necessary conditions for equality constraint. So x star is a local extremum of f, and it's subject to the constraints that h of x is equal to 0. So this should be a bold h of x. and let x star be a regular point. So again, we're assuming regularity of the constraints. Then there's some lambda, so that gradient of f plus gradient of h times lambda is equal to 0. Okay, we've just proved that in the previous argument. And a corollary, okay, a corollary is that if you define this new function, we're going to call this the Lagrangian. This is called the Lagrangian. If we create this new function that is called the Lagrangian, where we have f, and then we take h transpose times lambda. Okay, so h again, we're trying to solve this problem. Minimize f of x, subject to the constraint that h of x is equal to 0. Okay, so if I form something called the Lagrangian that has my f in there, right here, and then it has all my constraints, h transpose x. Okay, then x is a regular local extremum. If it's a local extremum, then when I take the gradient with respect to x here, what am I going to get? So in other words, this partial of L with respect to x, that's going to be the partial of f with respect to x plus the partial of h with respect to x lambda. Okay, so this guy is that, and it has to be equal to 0. So we know that the partial of L with respect to x at a local extremum has to be equal to 0. Okay, and we also know if I were to take this guy, if I were to take the partial of this guy with respect to lambda, what happens? So the partial of L with respect to lambda, well, it's just going to be h. And we have to have that's equal to 0 because that's our constraint. So if it's a regular local extremum, then both of these things has to be true. This is a necessary condition for it to be a local extremum. Wow, pretty cool, because this gives us now a solution technique. If I'm trying to solve this problem, I form the Lagrangian, and then I take the partial, just like I would, just like I know with an unconstrained problem, I take the partial of f and set it equal to 0 and find all of the x's, right? And that'll give me the points that are going to be extremum. So now I'm doing something that's very similar. I form this Lagrangian that has not just f, but my constraints and this extra variable lambda. Okay, now I don't know x and I don't know lambda, but I do know that if I take the partial of this Lagrangian with respect to x and set it equal to 0, and the partial of L with respect to lambda and set it equal to 0, that, if there's an x star and a lambda star that satisfy these two constraints, then x star is a regular local extremum. So this becomes a very powerful tool. So for example, let's solve this problem. Minimize x1 squared plus x2 squared subject to this constraint that x1 plus x2 is equal to 2. Okay, so let's just figure out what the solution is before we use our new technique, right? So x1 squared plus x2 squared is just a bunch of circles that are getting bigger and bigger. And then, in other words, level curves are a bunch of circles. So if it's equal to 1, it's going to be the unit circle. If it's equal to 4, it'll have radius 2, etc. Now, x1 plus x2, what is that? So that is, you could think of this as a line. x2 is equal to minus x1 plus 2. So it has a y-intercept of 2 and a slope of minus 1. So here's the y-intercept of 2, or x2-intercept, I guess, and a slope of minus 1. So this constraint, so we're constrained on here. So if I'm trying to minimize the norm of x subject to the constraint that has to lie in this line, well, the optimum is going to be right there, right? And it's going to be, it's going to be this 0.11. All right, so we know what the solution should be. Now let's try to solve it using Lagrange multipliers. Okay, so the Lagrangian is going to be, f, and since there's only one constraint, it'll be just lambda, this is like lambda 1, times the constraint. So the constraint can be written as x1 plus x2 minus 2 equals 0. So we have to write it in terms of an equal to 0 constraint. And there's our h. So that's f plus lambda h. All right, now I know that my necessary conditions say that the partial of L with respect to x1 has to be 0, partial of L with respect to x2 has to be 0, partial of L with respect to lambda has to be 0. So partial of L with respect to x1, if we go back here, this is going to be 2x1 plus lambda. 2x1 plus lambda, that has to be equal to 0. Partial of L with respect to x2, that's going to be 2x2 plus lambda. Whoops. 2x2 plus lambda equal to 0. And then the partial of L with respect to lambda, that's just my constraint back again. x1 plus x2 minus 2 equal to 0. All right, so from this equation, I get that x1 is equal to minus lambda over 2. From this equation, I get that x2 is equal to minus lambda over 2. And from this equation, I get that if I plug in what x1 is, it's minus lambda over 2. And x2, I get minus lambda minus 2 is equal to 0. So I can solve for lambda here. Lambda is going to equal minus 2. And once I have lambda, I can go back and solve for x1, 1, and x2 is equal to 1. So my optimal then is 1, 1, just like I expected from doing the example problem. So, in other words, we've made, look how easy we've made, solving this constrained optimization problem. We form the Lagrangian, and then we take the partial with respect to x and the partial with respect to lambda and set those equal to 0, and then solve for x and lambda. We have this extra variable, these Lagrange multipliers. And if we can solve those equations for x and lambda, then that has to be a local extremum. We don't know necessarily whether it's a local minimum or local maximum, but it will be a local extremum. Okay, let's do another problem. Let's suppose that x is a random variable with probability mass function. The probability that x is equal to xi is some pi. And then we can find the entropy of this random variable. The entropy is defined as h equals minus the sum of pi times log pi. This is a definition of the entropy of a random variable, discrete random variable. And now you might ask, what probability mass function has maximum entropy? So can I maximize this guy? So what I want to do is I want to solve this optimization problem. I want to maximize the entropy subject to the constraint that it's a probability mass function, meaning that the sum of the pi's are equal to 1, and each of the pi's have to be greater than or equal to 0. And what we're going to do is we'll ignore this inequality constraint and see if we get an answer where it's satisfied. So we'll just solve this as an equality constraint. Okay, so the Lagrangian looks like this. We have, F, which is the entropy. Notice that this entropy is a minus sum of pi log pi. So we have the entropy plus our Lagrange multiplier times our constraint. The sum minus, the sum of these things has to equal 1. So the sum minus 1 equals 0. Now I take my necessary conditions are that I take the partial of L with respect to each of these pi's, P1, P2 up to Pm. That has to be equal to 0. And the partial of this thing with respect to lambda has to be equal to 0. So the partial of L with respect to pi. So if I take just the pi, all of the other, pj's, the sum will go away. And I just have to take the log of pi log pi. And that's just going to be minus log pi. And then I take the, and then and here I'm going to get a, it's going to be, minus log pi minus 1. And then when I take the gradient with respect to pi here, I'm just going to get lambda. So this guy has to be equal to 0. So I can solve actually for lambda. And lambda has to be equal to 1 plus log pi. So log pi has to be lambda minus 1. And then I also have the constraint that when I take the partial of L with respect to lambda, I get the sum of pi's equal to 1, meaning all of the pi's. So each of the pi, since each of the pi's have to be are the same thing, then that means that pi is going to be 1 over n because they have to all sum to 1. So this solution satisfies the necessary conditions. So in other words, the maximum probability mass function, the uniform probability mass function, where they're all equal to 1 over n, maximizes entropy. So maximum entropy are where all possibilities are equally likely. Okay, so that's an example. Here's another example. Suppose I've got this. Suppose I have this an ellipsoid, and I have some point y that's outside the ellipsoid, and I want to find z in the ellipsoid that's closest to y. So what's this point? Given y, given my ellipsoid, what is z that minimizes this distance? Okay, so the equation for an ellipsoid is given by, remember, an ellipsoid is a quadratic form. So if L is actually, if I could take that quadratic and do a Cholesky factorization, and this thing would be so the ellipsoid is a set of all z's, so that z transpose L LZ is less than or equal to 1. That would be all of the points inside here. And I guess we'll probably set it. We're going to solve this as a. Let's see. I'll just kind of look here. We're going to solve this as a. In other words, if y is inside of here, then the nearest point is y. If it's outside, it's going to be on the edge, and so we're going to think of this as an equality constraint. Okay, so we're going to try to solve this problem. We're going to try to minimize the distance between y and z. And we're going to look over all z's, such that z transpose L z equals 1. So this means z has to be on the ellipsoid, and then we're going to minimize the distance between y and z, where y is a given. Okay, so if we form the Lagrangian, and the first thing we're going to do is make this a squared, because we can minimize the squared, the element that minimizes the square of the norm also minimizes the norm. And so we're going to call this guy F, and of course H is going to be Z transpose LZ minus 1 equals 0. So here's my Lagrangian. It's going to be, this is of course y minus z transpose y minus z. So my Lagrangian is F plus lambda times H. Okay, now the necessary conditions say that when I take the partial of L with respect to z and set it equal to 0, and the partial of L with respect to lambda and set all that equal to 0, that those points are a constrained extremum. Okay, so we take the partial of L with respect to z. Notice back here, I take the partial with respect to z, I get the partial, I get basically, this guy times the partial of this thing with respect to z, which is just going to be minus identity. So I'm just going to get negative y minus z. And then I have, when I take this with respect to z, I'm going to get lambda 2 L transpose LZ. So I'm going to have my, I guess this is a quadratic form, so it's going to be this guy times its derivative plus this guy times its derivative, so there'll be 2 of those. So I'm going to get a minus 2 y minus z plus 2 lambda L transpose L times z equal to 0. And then when I take the partial with respect to lambda, I just get my constraint. Okay, so the first equation here, if I solve for z, I'm going to have, so because of the minus sign here, I get a positive 2z, and I'm going to divide out the 2. So I'm going to get, z plus lambda L transpose L. So I can collect that as I plus lambda L transpose LZ, and I move the y to the other side. And then that implies that, I can solve for z by taking the inverse of this matrix times y. Remember, y is known and L is known. So, but I don't know lambda. So lambda has to satisfy, so now how do I find lambda? Well, I'm going to take this z and plug it in here and see what lambda has to satisfy. So I'm going to take this z, I plug it in, and there's my constraint. So lambda, notice everything in this equation is known except for the scalar lambda. So I have a scalar lambda here, and I have to find lambda that satisfies this. So it has to be solved numerically using some kind of root finding technique like Newton's method. Okay, so but once I find lambda, so I do some numerical root finding technique, I find lambda, and then that'll give me z. So my problem is done. I've basically replaced this optimization problem, trying to, and this is in any dimension, right? Finding the closest point. I've reduced it to a one-dimensional search. So I have to do this one-dimensional search using it's not even a search, it's a root finding problem that can be solved very quickly. Okay, here's another example. Consider this optimization problem where we have a quadratic form, 1/2 x transpose ax, subject to a linear constraint, bx equals c. Okay, so the Lagrangian, I'm going to have f plus, now this is a set of constraints, so I'll have lambda transpose bx plus c. And my necessary condition will be the partial of f with respect to x is equal to 0, partial of f with respect to lambda equals 0. So when I do my necessary conditions, I take the partial of L with respect to x. Notice, this is going to give me an ax, and with respect to here, I'm going to get a b transpose lambda. Okay, so I get ax plus b transpose lambda is equal to 0. And then when I take the partial with respect to lambda, I just get my constraint back, bx minus c equal to 0. So if a is invertible here, then I can invert and solve for x. It's going to be the minus a inverse b transpose lambda. And now I can plug that equation for x in here. So I'm going to have a minus b a inverse b transpose lambda is equal to c. And if this guy is invertible, then I can solve for lambda, as a minus this matrix inverse times c. And then I can come back and plug that in for x. So x is going to be this guy. I'm just plugging in what lambda is here. And it turns out that, notice, this guy looks like, remember, your least squares, I guess if A is identity, notice that In other words, if I come back here, notice that if A is identity here, so if A equals identity, then this is 1/2 norm of x squared. And we're solving a min norm problem, right? You're minimizing the norm subject to a linear constraint. And notice that in that case, A is equal to identity, you would get, this thing looks like B transpose inverse C. And that's just our pseudo norm, or pseudo inverse for min norm problems. So A inverse becomes the weighting, and this is just a weighted norm pseudo inverse, but obtained very nicely with Lagrange multipliers.